take a look at today's lesson. We actually have two topics today. The first one is algebraic substitution, and the second one is a version of Riemann sums. So let's work on the first one, algebraic substitution. So when we do a U sub, you know, we figure out what we want to make U, then our derivative is there, and everything just kind of clean wipes, it's all U du. There are some instances when we do that where we actually have some x's left over. And doesn't necessarily mean that U sub won't work, it just means that you may need to try algebraic substitution. It's really kind of like a second substitution. So we'll do the regular U substitution, and then we will actually substitute again. So let me kind of go through the process and show you. It's like on the first one. So we look at that and we think, okay, well, U is 2x minus 1, right? That's what we would make U. So U would be equal to 2x minus 1. Then du would be 2 dx, so 1/2 du equals dx. So let's kind of go through here. We would have this portion would be taken over by the u, and then this dx would be taken out by the 1/2 du, but notice how we have an x left over. We have an x left over. When that happens, we should try this algebraic substitution technique. It won't always work, and if it doesn't, that means we need to try different, which we'll learn next semester, a different integration technique. But what we would do is try. So what we have established here is a relationship between u and x. Our substitution, we related u and x together. I've used this portion of it. But what if I solve for x? Then I would get an expression with u in it. So that's actually what I'm going to do. That's the algebraic substitution. I'm going to take this and solve for x, and then replace this x with what I get, and see if it works. Okay, so let's do that. So we would have u plus 1 equals 2x, where x is 1/2 u plus 1. All right, so now this portion right here, this piece is going to go replace that x. We're going to take that and we're going to put that instead. So what I have this 1/2 from my u sub portion, and I have this 1/2 from my algebraic sub portion. And I'm going to put them outside the radical, or outside the integral. So we're basically going to have a half times a half, or 1/4. So we have 1/4 outside there. So replacing the x is going to be this piece right here. I already have the 1/2 here, so the u plus 1. And then replacing this would be u to 1/2. So hopefully we recognize we can't integrate it in this form. We're going to need to rewrite it. So I need to distribute. And that's really the only time this doesn't work is if what we have left over we can't integrate. It could happen. This we can actually integrate. We can distribute the u to the 1/2, and we would get what, u to the 1, so 2 over 2 plus 1 over 2, 3 over 2, and u to the 1/2 times 1 would be u to the 1/2. All good? So now let's do our reversal power rule. Let's go ahead and integrate. So we have 1/4 times, let's see, add 1 to 3/2, we get 5/2, divide by 5/2, multiply by 2/5, u to 5/2, plus, add 1 to 1/2, get 3/2, so plus 2/3 u to 3/2, plus c. Back to plus c. Alright, so I'm going to actually do two things at once. I'm going to distribute this 1/4, and I'm going to put the u back in all at the same time. Hopefully that's not too troubling. So I'm going to do that all in one step and get 1/10 times my u is 2x minus 1 5/2 plus 1/6. 2x minus 1 to the 3/2 plus c. And that is our very first algebraic substitution. How's that? Okay. Well, let's look at our next one. So on this one, 1 plus x squared would be kind of where we would go to do a u sub. So u is 1 plus x squared. So du is 2x dx, or 1/2 du equals x dx. That's my u sub part. So this portion right here is my u, right? And I actually only need 1x for my derivative. I just need one of those. I have 5 of them. So I'm going to have to, let's think about it this way. I have this one I'm going to take care of with this. But the other 4, there's 4 right there, I've got to try to do an algebraic substitution with. I've got to try to get rid of them by looking at the relationship that I've already established between u and x and using that relationship to solve for x. So I'm going to move the 1 over, and since I need 4 x's and there's 2 here, I'm not going to square root. I'm not going to go all the way to x because I need 4 of them and here's 2. So basically I need 2 of these, or I need 2 of those. I would replace those 4 x's with 2 u minus 1's. All right, so let's do that. Let's go through that substitution. So I have this 1/2 from my u sub part. Let's see, then we would have u to the 1/2 in here. And I have 4 x's, so we need 2 of these. Du. Okay. So at this point, again, we can't integrate it like that. We're going to have to, do algebra. We're going to FOIL it, distribute the u to the 1/2, get everything all worked out. And I did that already. I'm not going to go through the algebra, but I had already done that. So when you do that, when you FOIL this out, then distribute the u to the 1/2, you will get u to the 5/2 minus 2u to the 3/2 plus u to the 1/2. All right. So now let's integrate. So we have 1/2 times the integral of u to the 5/2 is 2/7 u to the 7/2 minus 2 times. The integral of u to the 3/2 is 2/5 u to the 5/2 plus 2. The integral of u to the 1/2, we add 1 to 1/2, get 3/2, so 2/3 u to the 3/2 plus c. Okay? All right, so we're just going to do actually a couple things at once. Okay, I'm going to distribute this 1/2, and I'm going to put this u, the 1 plus x squared, back in. Okay, we'll do all of that at once. And probably have to use more than one line. That's okay. So I get 1/7 times 1 plus x squared to the 7/2 minus, and multiply all that together, and I get 2/5 times 1 plus x squared to the 5/2 plus. Then we get 1/3 times 1 plus x squared to the 3/2, or I might almost say plus c. And we got our plus c. Okay, so that is our second algebraic substitution. All right, let's look at the very last one on here. Move this up a little bit. So here, We think we can see u would be 2x minus 1. du is 2 dx, so 1/2 du equals dx. Okay, so this is going to turn into a u, and I have an x, an extra x. So I'm going to have to try the algebraic substitution again. I'm going to take the relationship that I have between u and x, and I'm going to solve it for x. So let's see, that would be u plus 1 equals 2x, or 1/2 times u plus 1 equals x. Okay. So I have two halves again. I have this half from my u sub, and I have this half from my algebraic substitution, which is going to make a fourth, right? I'll pull out a fourth. Okay, oh, I'm going to have to change my bounds. All right, let's change our bounds. Let's go up here. So let's see, we have u equals 2 times 1 minus 1. That's my lower bound, or 1. My upper bound, u equals 2 times 5 minus 1, or 9. So I have those bound. And again, I think we've talked about this before. You don't have to write out that work. If you want to do that in your head, you certainly can. I'm just writing it out so we're all clear, make sure we know how we got those numbers, right? The 1 and the 9. So I'm going to keep it with u's, and my new bounds are 1 to 9. So let's see. In the numerator, we had 1 plus 1, u plus 1, and the denominator is u to the 1/2. Now we can't integrate that. We've probably encountered those before, where we need to rewrite that. There is no quotient rule in integrals. So if I wrote this as two different fractions, I could do my reversal power rule. So let's just think about it as two different fractions. So 1/4 integral of 1 to 9. So u to the first over u to the 1/2 would simplify to be u to the 1/2 plus 1 over u to the 1/2 would be u to the negative 1/2. And that's what we'll integrate. Right, so we have 1/4 times the antiderivative of u to the 1/2. Let's see, I have 1 to 1/2 is 3/2, so 2/3 u to the 3/2 plus, we add 1 to 1/2, and we get 1/2, so plus 2 u to the 1/2. And now this we would evaluate from 1 to 9. Now we have done several days of that, and just for time's sake for the lesson, I'm not gonna do the f of b minus f of a right now and do all of the arithmetic. I'm just going to tell you that if you were to do that, f of b minus f of a, work it all out, you should get 16/3. 16/3 would be the answer that you would get.
Okay, so let's take a look at today's lesson. Today's lesson, we're going to look at particle motion again. We looked at particle motion several weeks ago, probably more over a month ago, with relation to derivatives. At that time, all we knew was how to take derivatives. And we talked about particle motion in that context. So I want to remind you what we did. It doesn't mean that we're going to not ever do that again. It's just we're going to have a different way also to do it. So when we had the derivative and we wanted to find displacement, we really actually needed the position to find displacement. We couldn't have just had the derivative back then. We would need the actual function. And to find displacement, if you recall, we just did end minus beginning of the actual position function. Remember that? So if we were, let's just say we were looking to find, from say t equals 0 to t equals 3, of some kind of function. Let's say we were looking to find the displacement of, the particle that was moving. We would have done s of 3 minus s of 0, right? That would have given us our displacement. Remember that? That's what we would have done. When we had to find distance, if you recall, that was much more difficult because we know that the particle can move, right or left. And then when it moves left, it has a negative It's negative, and so that would be a problem for us with distance. It would like negate that part. So if you recall, we like found the derivative, or we had it and we set it equal to 0, and we did a sign chart. Let's say in this case, you know, let's say 2. Let's say that's what our sign chart was. Between 0 and 2, it was negative, the velocity was negative, and between 2 and 3, we were positive. And so what we did then is to find the distance, we took each section. Recall, remember we did the absolute value of end minus beginning, like absolute value of s of 2 minus s of 0 plus. So absolute valuing it would negate, you know, get rid of that negative. And we don't really have to do the absolute value of the second piece, but that's just what we did. So s of 3 minus s of 2. And that would have given us our distance, right? This gave us distance, and this gave us displacement. Okay, that's before we knew how to integrate. Are you with me? And you can still do that. That's still a viable technique. But now we know how to integrate, and we have more options available for us. We don't have to just rely on these two options. If we want to find displacement, what we can do is use this formula. Okay, so I would integrate from my beginning time to my ending time of my velocity. Integrating velocity gives me displacement. That's what it does. So let's look at this picture over here. If I want displacement, I would simply, you know, collect or accumulate the area under the curve all the way across, going forward. If it was above the x-axis, it would be positive. If it was below the x-axis, it would have a negative sign. I would just accumulate the whole thing, right? And that would give me my displacement. Okay, so that's how to do it with integration. We would need, now this is important, we need velocity to do the integration for. Remember when we first started doing integration, I explained that like aha moment I had when I'm like, how in the world can area be distance? Or we had, if this is our rate, see our velocity is here, our rate, and this is our time. The rate and the time is that product is our distance, that area is the distance. So with displacement, we treat, you know, above the curve, under the curve, we just treat it as it is, positive, negative, positive. If we want distance, though, it becomes a little bit more difficult, just like without the integral, right? It was more difficult with just derivatives. It's a little bit more difficult. We actually have to do the absolute value of the velocity. That's what we have to do if we want distance. So looking at this graph right here, what I would have to do is I would have to alter this piece and force it to be positive if I wanted distance. So I would have to force it to be positive to get my distance traveled. And that's what this absolute value does. It's the absolute value of velocity, not of the result. So some students want to put the absolute value on the outside of here. That really doesn't do anything except for make our displacement positive. I would need to absolute value the actual velocity function and force it to be positive all the time. Okay, so that's how we would do distance with an integral. Again, we're integrating velocity. And actually, when we integrate just regular old velocity, that's displacement. When we integrate speed, so the absolute value of velocity is speed. When we integrate speed, we get distance. So those are two really important concepts for us to kind of absorb and really think about when that happens. So this is it in words. Integration velocity over time produces displacement. Integrating speed over time produces distance traveled. Okay. So these two formulas right here, those will certainly be on formula quizzes. Those are important formulas. We need to know how to find displacement using an integral. We need to know how to find distance using an integral. So those will be on formula quizzes. Okay, these aren't going to be on formula quizzes. Really, this is just highlighting a relationship, the relationship between velocity and position. If I integrate velocity, I get position. I mean, it's just talking about the relationship. That kind of is like common sense to us right now. If we integrate velocity, we're going to get position. If we integrate acceleration, we're going to get velocity. So these are formulas that they're not going to be on a formula quiz. They're just talking about trying to highlight the relationship between those types of functions. That's all. Okay, are we okay with that? This formula you would have probably memorized in, pre-cal or algebra 2. This is on particle motion, this formula, where t equals 0 at the velocity at time t equals 0, so that's our s naught, our initial position, and v naught, our original velocity, initial velocity, would go here and here. And that number, that a, remember that was acceleration due to gravity. Remember that from back when? Acceleration due to gravity, if we're in meters, it's 9.8 meters per second. If we're in feet, it's 32 feet per second squared.